Good evening, everyone. I'm Daksh Tilani. Currently, I'm pursuing Computer Science and Engineering from Vellore Institute of Technology, Chennai. So today, I will be discussing a bit about application of finite automata in network. So, what is an automata? So, before going deep into automata, we must see from where it has originated from. So, the word automata comes from the Greek word automata, which means self-acting, self-built, self-moving. An automata is an abstract self-profiled computing device which follows a predetermined sequence of operations automatically. An automata with a finite number of states is called a finite automata or finite state machine. Basically, in simple words, an automata is any system which works by itself without any human interference. So there are different types of automata. Broadly, it is divided into two parts, finite automata and infinite automata. Finite automata means the automata having finite number of states, and infinite automata means the automata having no infinite number of states. So in finite automata, we have non-deterministic finite automata and deterministic finite automata. Whereas in infinite finite automata, we have push-down automata. So now introduction to automata theory. So basically, automata theory is a branch of computer science and mathematics that deals with the study of abstract machines, which are capable of performing computation. So after automata, it is very important for us to learn about introduction of automata theory. These are abstract machines and they can be used to model and analyze the behavior of complex system and processes. So there is a cycle conversion that represent that if we have a language, then from a language we can get a null NFA. From a null NFA, we can get an NFA. From a NFA, we can convert a NFA into DFA. And from a DFA, we can get a regular expression by Arden's theorem or any other method. And from the regular expression, we can get a language. So this cycle goes on and we can get our desired results. So there are various applications of automata theory. Some of them are they are used in compilers, interpreters, parsers, and preprocessors. Natural language processing, that is, it is the ability of a computer to program to understand human speech as it is spoken. So natural language processing is a component of artificial intelligence. Next, the automata theory is actually the heart of TCP or IP protocol is a finite state machine. So in TCP or IP protocol, finite state machine is used. It is also used in text processing. You probably often use your text editor to find some text in a file. So where a program is defined or email that you have sent before, you can check it. And this also requires a finite state machine. So finite state machines are often used in AI side of game program. They turn out to provide an excellent model for encapsulating character behavior. For instance, an enemy might have states representing patrol, search, approach, attack, defend, retreat, die, etc. So an enemy can take any of the state at any time. With this well-defined transition between them, this doesn't involve any format aspects of automata like regular languages and the like, but the concept of automata is very core one. It develops solution for constraint programs. So this is also one of the major applications. Now, applications of automata theory in networks. Till now, we have discussed various fields in which automata theory is used. But now we are going to discuss specifically that how the automata theory is used in networking and communication. So network using some specific protocols to transmit and receive data. The protocol used are error control, flow control, bandwidth limitation, etc. So to solve this problem, we require the definition of one or more communication protocols. That is shared convention for the transmission of data in one direction and acknowledgement that data has been received in the other direction. So consider it there is a sender and a receiver. Then we must have shared convention and acknowledgement to transmit the data successfully. Rather than attempting to describe all of the practice, the required functionality of a single protocol, it is now common practice to provide a protocol stack. Protocols at layer N of the stack make use of the functionality provided at layers n minus 1 and below. For example, Internet Protocol stack has 5 layers. First one is the application layer, next is the transport layer, third one is the network layer, fourth is the link layer, and fifth is the physical layer. So here, this diagram represents the basic protocol used in transmit. So in this diagram, the horizontal line, the swing, represents the time, and the sender sends some data and is received by the receiver. So here, as the time proceeds, as the sender sends the data, it is received by the receiver at this point of time. So the finite state model of the sender and the receiver using this protocol are very similar. In constructing this model, we assume that there is a high level process on one side that invokes sender when it has sent data, and high level process on the other side that will be notified by the receiver whenever the data is received. So there is a process which tells the sender to send data, and there is a process which tells the receiver that data has been received. So although we won't handle this part of the process in the models we are about to build, we can note that sender will maintain a FIFO queue of messages that it has been told to send. Each time it is ready, it will remove and send the message at the head of the queue. So suppose sender is sending messages, so it would be in a FIFO fashion. The request or the data would be stored in a FIFO fashion in the queue, and then it will be sent to the receiver. Then to analyze this problem, we can also come up with a DF. So there is a DFF for sender. It is initialized to the waiting state here. So the sender waits until it is given data to send. So here the sender is waiting until the instruction to send the data is not come. So as the instruction to send the data came, it will accept the data and move to the active state where it will send the data and come back to the waiting state. At that point, its state changes, sends a data message, and then returns to the waiting state. It receives the interrupt, and then it will send the data and come back to the waiting state. Whereas in the receiver end, it would also be initialized to the waiting state only. After the data is being received, it will go to the active state, and after delivering the data, it will come back to the waiting state. So the receiver wait until the data arrives. So here it will be waiting until the data is arrived. When that happens, it moves to the active state in which it delivers the data. When it finishes, it returns to the waiting state. So after receiving the data, it will deliver and again come to the waiting state. So there's another one application, that is application is stop and wait protocol. So another widely used protocol in the network is stop and wait protocol, also known as automatic repeat request or an ARQ. So an ARQ protocol, the receiver communicates back to the sender, and the sender exploits that communication to help it determine when a failure has occurred and the message should be retransmitted. A simple subfamily of ARQ protocols is called stop and wait. So in this diagram, the sender is sending the messages which is received by the receiver. As it is received successfully, then the receiver would be sending the acknowledgement to the sender that the transmitted data has been successfully received. For this problem also, we can also come with the DFA. Here, as we discussed in the previous slides, that here you will be waiting for the instruction to give data or transmit data. So same is here. It will be waiting for the data to transmit. As it gets the instruction to send data, it will come to the active state. From there, it will send data. If the data is received or sent correctly or fully, then it will give the acknowledgement to the sender. Otherwise, if there is a timeout, then the sender has to again retransmit the data. So the sender will never send a second message until it knows that the receiver has successfully delivered the data from the first one. It will not send another data until this acknowledgement is there. Also, in the receiver end, it would be receiving, waiting till all the data is received. As the data is received, it will move to the active state. In the active state, it will deliver, and then an acknowledgement will be sent to the sender to receive the next instruction. So It solves one error control problem. If a data message is lost, the sender will retransmit it after it times out, waiting for an acknowledgement. So if it time out, then the sender has to again send the or retransmit the message. So here is the key. And if the translated message is corrupted and the receiver can tell that, for example, by using checksum bits, the receiver can simply fail to send an acknowledgement, then sender will time out. If this receiver fail to send the acknowledgement, then the sender will be timed and the message will be resent. There are also variants of stop and wait protocol in which explicit negative acknowledgement messages are sent when message arrives correctly. So the alternating bit protocol doesn't add arbitrary subscript. It does add a single control bit to each data message and to each acknowledgement. The bit will alternate values with each transmission by convention. The receiver will flip the bit before sending an acknowledgement. So the message acknowledgement, the receipt of do will be acknowledged vice versa. So here we can see the sender is sending the data, but this is the ideal case first. The sender is sending the data and it is received by the receiver and it is sending the acknowledgement back to the sender. But suppose in the case if due to any some noise or disturbance, the sender is transmitting data, but it is received by the receiver at this point of time. Then there is a copy of data. See, timeout is there. So there will be two copies. The data received by the receiver will be here. Then only the acknowledgement will be sent. And this acknowledgement would be transferred, but no other further classification will be there. After this, to describe the behavior of senders and receivers that exploit this new protocol requires two copies of each of the state that were needed to stop and wait protocol that was defined here. And one copy corresponds to the handling data whose control bit is 0 and the other handling data whose control bit is 1. So here it would be changing. The here would be complicating the value. Here would be 0 and after complementing it would be 1. So one there would be two duplicate copies and whose one copy correspond to handling data whose control bit is 0, the other handling whose control bit is 1. For this, we can have a DFO, which can be seen here. The sender would be initialized to the waiting state as it is there. It will be starting with the waiting state. As it gets the data to transmit, then it will accept data and come to the active state. After coming to the active state, it will send the data and it would be waiting for the acknowledgement. If it gets acknowledgement, then it will go another for waiting to get another data to be transmitted. If not, then it will be timeout and after that, it would be delivered and again waiting for the acknowledgement. And after that, if it again get the data to be transmitted, then it will go to the active state and other and send the data again. Similarly, for the receiver end, it would be initialized to the waiting state. As it get the data, then it would be receiving a data, it will go to the active state. Then it will deliver data and come to the replying state. If it get the acknowledgement, then it will move to the waiting state. There also it will check if it can deliver data, then it will go to the active state and then deliver. If it get the acknowledgement, then it will be waiting for another data to be coming and then only it will go to the active state. If not, then it will be in the waiting state. So here both sender and receiver are initially in the waiting state. As I told, both will be in the waiting state initially. So thank you. That's it. I think I hope you would like the video. Thank you.